disaster risk reductions. Recently, every year we experience very severe rainfall disasters, especially very big is July 2018 and also 2019. 2018, this was a rainfall event, and very severe rainfall happened western, very wide area, western part of Japan. And 2019, very big super typhoon hit east and northern part of Japan. And these provided record-breaking rainfall, and damage was huge. In 2018, 237 unfortunately, people lost their lives and 8 missing, and levee breaching, total 73 levees, and 2019, 99 deaths and 3 missing, and levee breaching is huge, 140, and economic losses in this 2019 flood was record-breaking, 2,180 billion Japanese yen. So the impact assessment of climate change on hydrologic extremes and adaptation strategy planning by policymakers is very, very urgent issue. So today I'd like to talk is, at first I'd like quickly to talk about DHOPDF. This data was a large ensemble climate change projection data developed by Meteorological Research Institute. So the characteristics of this DHOPDF is very large ensemble number of the data. This is very important. And then impact assessment. Civil engineers or water resource engineers, flood and inundation modeling and flood projections, and impact assessment of climate change on flood risk. And then this information goes to government of the Japan policymakers, adaptation strategies. The government of Japan has decided to incorporate climate change scenario data into flood control planning, and already began to review the flood control plan. So I'd like to talk about this very in this next 10 minutes. At first, DHOPDF data. So this covers entire globe with 60-kilometer resolution, and eastern part of the area, 20-kilometer resolution data. So this is a simulation area settings, and experimental design is, one is 2-degree increase scenario data, and also extreme cases, 4-degree increase scenarios data. And very important characteristics is for 60-kilometer resolution data, we have opportunity to use total 6,000 years time series data. This long time series data is very, very important to evaluate very, very rare extreme event. And 4-degree increase scenario, this is also we had opportunity to use 5,400 years time series data. So these very, very long time series data with ensemble member, this was a very important characteristics of DHOPDF data. Then I'd like to quickly talk about what kind of information we can obtain by using this data. We applied this rainfall data into all over the Japanese catchment. And I would like to talk about the result focusing on Yodo River Basin. This covers Osaka and Kyoto area. So these are the second largest city area in Japan. So this figure shows that left-hand side, this shows x-axis is annual maximum 24 hours rainfall data, and y-axis is non-exceedance probability, and this and also return period. So you can clearly see that this blue dot is this was the relationship between historical climate, 200 years, 200 millimeter per 24 hours, and this non-exceedance probability is about 98%. This means about 80 years return period. So this relationship, this blue is simulation data come from DHOPDF. And quite nice is we have total 3,000 years data, so we can have this line, and black dot is observation data. So this matches very well. And then very important thing is this red line shows under 4-degree increase scenarios. So this clearly shows that future 200 years rainfall becomes much more bigger. And our finding is currently 900 years rainfall is also, we can evaluate by using this data. And 4-degree increase scenario, 200 years rainfall is higher than 900 years rainfall. And left-hand side is we give this rainfall into rainfall runoff model, and also we can evaluate the relationship between discharge and non-extinction probability. And this is also without doubt, we can see that 4-degree increase scenario, river discharge becomes much more higher. So this is entire Japanese catchment, and the x-axis shows river-based index, 1 to 3. This is the north part of the catchment, and 100 and 100, 101, blah, blah. So this is the southern part of the catchment. And this shows how the annual maximum peak discharge will increase. This y-axis shows the ratio. Northern area almost doubles, peak discharge becomes double. And this is shows the range estimated by sea surface temperature ensembles. And southern part, Kyushu and this area, this is also 1.5 times higher. So we are really, we need to recognize that this increase, this is very serious. And also this is simultaneous flood probability under 4-degree increase scenario. So this means, for example, more than 5 catchment experience flood disaster at the same time, same years. This probability is around this, but current climate, something like this. So this is exceedance probability. So blue line is historical climate, current climate, and red one is 4-degree increase scenario. So this is clearly indicates that the catchment we experience the flood at the same time because much more higher. And flood risk, for example, inundation disasters. Through the inundation, through the subway, very, very extreme cases, flooded waters go to the different area through the subway. This was expected. And also what we have done is to obtain the relationship between economic damage and exceedance probability. So by using inundation simulation, it is possible to estimate these evaluation how we experience damage in a probabilistic way. So how to cope with it? One is very important is real-time flood prediction, and also strengthening of flood control capacity by dams. Now we are doing this technological improvement. So one is rainfall runoff model for all over the nationwide catchment. So this is the example now on a real-time basis, 150-meter resolution rainfall and inundation model is now we are operating, and we look at the maybe this will be hopefully future. This will be installed to all over the Japanese area, and also dam reservoir operations. So if we have ensemble predictions, at least this is a minimum maybe predicted inflow, and this is ensemble medium, and this is maybe ensemble maximum. So we have these prediction with uncertainty. Then based on this information, at least we can pre-release the dam reservoir storage, because at least this water will come to the dam reservoirs after the flood. So much more fully utilize the dam reservoir capacity. These ensemble prediction, real-time prediction is also very important. Then remaining time, I'd like to introduce Japan's new policy on water-related disaster risk reduction. The name is River Basin Disaster Resilience and Sustainability by all. Last year, the government of Japan changed their policy, and this is a new policy. I'd like to quickly talk about the content of this new policy. The background is I have talked that impact of maybe climate change and very big flood disaster happen every year. And also social trend, Japan facing declining of the population and also aging population. So this is very, very increase the vulnerability of the relate for the natural disasters. And at the same time, we have opportunity to fully utilize new technology for new prediction. So in this situation, without doubt, flood intensity will increase. Then how to cope with? One is transition to river basin disaster resilience and sustainability by all. This means for a long time, Japanese basic policy is to construct dikes or dam reservoirs. And when the very big flood happened, to flow the flood water very quickly through the rivers. But unfortunately, due to the climate change, the rainfall increase and river discharge increase. So it is not easy to flow the water only the rivers. So many people related to the river and the land need to cooperate each other. So this means by all. And revised plan for flood control means currently Japanese government only used past historical precipitation data or tidal level record. Only observation data is used, but new plan consider the impact of climate change, for example, rainfall increase and also river discharge increase. And many researchers have done this research, and also the governmental researchers is also analyze the future change of precipitation and river discharge. Then government clearly recognize that it is important to incorporate the future climate change scenario data into this flood protection plan. So this too is a very big change happened in recent years. So Professor Anurag and everybody, thank you very much for listening to my presentation. Thank you.
Yes, thank you very much, Professor Tachikawa. So